Dr. M.A. Bhagaveni, Professor, Department of Electronics and Communication Engineering, College of Engineering Gindi, Anna University, Chennai. Dr. M.A. Bhagaveni graduated from Government College of Technology, Coimbatore, has completed her Masters and PhD at College of Engineering Gindi, Anna University. Her field of interest includes cognitive radio, ad hoc networks, wireless sensor networks, and wireless communication. She has completed 2 projects, one for CVRDE and the other for DST. She is the recipient of Young Scientist Award from DST. She has got 2 Best Research Paper awards in international conferences. She has published more than 70 research papers in reputable journals and conferences. She is author of 2 books. The one is Analog and Digital Communication and the other is Cognitive Radio, an Enabler of Internet of Things.
Welcome to the UGC lecture series. The content of this flow is observation, inferences and results. Then you need to write the procedure. The procedure here is nothing but the circuit connection is made as shown in the circuit diagram. Connect a power supply to the collector of the transistor, set the function generators connected to the base of the transistor as carrier voltage 6 volts, frequency 500 kilohertz, set the function generator connected to the emitter of the transistor as message signal Vm equal to 60 millivolts and Fm equal to 1 kilohertz. You get the modulated output at the output of the collector of the transistor. Observe A max and A min from the output waveform. Compute the modulation index value mu. This is first step. You can repeat it as many times as you want. And there are certain things that you need to see with respect to AM modulation. That the conditions here are, one of the most important thing is you can set up the output, the message voltage to be equal to that of the carrier voltage. So, at that instant how the waveform will look like, right. You can just this observation, right, you can observe many different values. So, one of the critical observations that what you can make is, one is when your message voltage is exactly equal to collector voltage. The other type is whenever your message voltage is very much greater than your collector voltage. For these 2 cases, you just see what is the modulation index and what is your how the waveform will look like. This is the case for mu less than 1. We have done 2 values and plotted in the table. When you just look into this waveforms, this is the case for mu less than 1. When mu equal to 1, that is whenever your Vc equal to Vm, will be having a waveform like this. Whenever my Vc is equal to Vm, we will be having a waveform like this. So, you can just see V min here is equal to 0, right. You get a value for V max, but V min will be 0. So, when you substitute into the formula, V max minus V min, which is 0, divided by V max which is 0, finally you get V max by V max, which is the same value that you are going to divide, which is nothing but 1. So, this modulation is called as critical modulation. The point at which V min goes to 0 is called as critical modulation. So, the amplitude of the carrier will become the amplitude of the message signal. So, if the second case where we are going to increase further for this case, my Vm will be very much greater than the Vc. The message voltage will be very much greater than the carrier voltage. So, for this case we can see there will be a phase reversal in the carrier. So, your waveforms will be carrier. So, at this point the carrier reverses its phase. So, this is called as over modulation. This is critical modulation, this is over modulation. You can just observe, draw the waveforms, write down the modulation values or tabulate the modulation values. To get the critically modulated AM waveform, we need to adjust the message signal amplitude to be equal to the carrier signal amplitude. Once we do that, we get a modulated waveform which will just look like symbol 8, horizontally placed symbol 8. So, now when we measure A max and A min, just you have to move the cursor to the maximum point. Del y value is 1.44 volts. This is your A max under critically modulated for the critically modulated signal. A min for this critically modulated signal will be, just bring down the cursor, keep it at the minimummost point, see the del value is about 0 volts. The upper arm coincides with the lower arm of the modulated signal. So, the symbol is looking like 8. So, the minimummost point, the A min will be at the coincidence. So, you can see that the A min will be equal to 0. Now, when you substitute in your modulation index value, A max will be 1.44, A min is 0 divided by A max plus A min, which is 0. So, 1.44 divided by 1.44, you get modulation index to be equal to 1 for this type of waveforms. We can also see the waveform for modulation index greater than 1. By just increasing the message signal amplitude greater than the carrier signal amplitude, this is your over modulated AM waveform. The over modulation is nothing but mu is greater than 1. In the sense, the negative part goes below the reference line. So, here you will be having the phase reversal. Here you can see the phase reversal part of the over modulated signal. So, the envelope tract is not equal to the voltage value of the message signal. So, for AM modulation, we need to keep in such a way that the message signal amplitude is always less than the carrier signal amplitude. So, this is how we measure the modulation index of the AM modulated waveform. Similarly, we can go and see what will be the frequency of operations of the AM modulated waveform. I just set back to the mu less than 1 and we will see how to measure the frequency of operation for the AM modulated waveform. Now, it is a modulation index less than 1. So, DSOs have the facility of viewing the frequencies, that is when you put the, you can go to the math operation and just click FFT part of it. Now, we can see this is the frequency response of the AM modulated wave, where you can see the center carrier frequency followed by FC plus FM and FC minus FM. This is the value what is displaying, this is the center carrier frequency. So, 93 plus 2 will be your upper side band. Can be just see, you can place the cursor at this of your second peak here. 93 plus 2, it is about 95. 95 kilohertz is your upper side band. When you just move on, this is the peak at which your lower side band occurs, which is about 91. Lower side band is occurring at 91. So, this is the frequency response of the AM modulation. Amplitude demodulation. So, once your modulation process is over, you need to demodulate. The theory behind demodulation, you can write a few steps like the process of detecting the modulating signal from the modulated signal is called as demodulation. Demodulation is a reverse process of modulation. The detector circuit is employed to separate the carrier from the and eliminate the side bands. So, that is the main thing, you will be detecting the carrier, separating the carrier, you are going to eliminate the carrier and get back your message signal. So, that is the main part of your amplitude demodulation. So, while constructing demodulation circuit, you should be very careful with the time constant called as RC. An increased time constant RC will result in marginal output which follows the modulation envelope. If you further increase the time constant, the discharge curve will become horizontal if the rate of the modulation envelope during negative half cycle of the modulating voltage is faster than the rate of the voltage RC combinations. So, the output fails to follow the modulation resulting in distorted output. This is called as diagonal clipping. This will occur only when the modulation index is very high. So, how can you exactly demodulate AM waveform is, you need to be very careful in selecting the RC. RC is the time constant of the circuit. The depth of modulation of the detector output is greater than unity and the circuit impedance is less than circuit load. Circuit impedance should be less than circuit load will result in clipping of the negative peaks of the modulating signal. This is called as negative clipping. So, to exactly reconstruct, you should be very careful in RL, you should be very careful with RC. So, while you are selecting your circuit load, the circuit impedance should be very much less than the RL. So, very large RL should be available and the time constant RC should be carefully chosen, for it can follow the message signal. The operation of this circuit for AM demodulation is, this is your modulated waveform. We have a diode, a capacitor, this is the capacitor and this is your load resistor RL. We are going to measure the output across these 2 points. This is my AM modulated signal. So, whenever the AM modulated signal passes through the diode is going to act as a rectifier. So, it will conduct whenever this is your positive side, this is your negative side. Whenever the positive side is going to have a higher voltage compared to this part. So, compared to this voltage, whenever this voltage is higher, the diode will conduct. This will be in the forward bias, so it will conduct. Whenever the diode conducts, there is a capacitor you are going to see here. This capacitor will start charging to that voltage. So, once this charges up, so this voltage will become higher compared to this voltage. So, the diode will not conduct. So, at that instant of time, whatever the capacitor has stored will start to discharge through the load resistor RL. So, the charging is through forward resistance of the diode and the capacitance, discharge is through load resistor RL and the C. This is the discharging part, this is the charging part for the capacitor. So, when these two are properly happening, we are going to see a modulated waveform output. We are going to see the modulated waveform output. Right. So, here we are going to have a AM modulated waveform like this. I have drawn only the positive part of the positive half cycle of the carrier modulated waveform. So, initially the charge in the capacitor will be 0. So, diode will conduct, the diode will conduct from this end to this end. As it conducts, the capacitor and the charge will also charge up. So, now it has reached the peak. After this point, the signal is decreasing, which means that this part of the voltage is greater than this part. So, the diode will not conduct. What will happen here? The capacitor is going to discharge. So, it will just discharge through this value, through this RL. So, as it discharges, once again the voltage here rises, once again the voltage at the input voltage it rises. So, till that point it will discharge. As the voltage rises, this becomes more positive compared to this end. So, it will try to capture up. Once again the voltage in the capacitor will capture up, recharge. So, discharge, recharge, discharge, recharge. So, this will continue in such a way that this will follow the amplitudes of this will be like this. Finally, you are going to follow the amplitude of just pick up the peaks of the carrier waveform. So, that is what the circuit will do. So, that is how you are demodulating your message signal. So, you can remove away the ripples here, small ripples here, by carefully choosing the RL values, RL and the time constant RC. So, this is the operation of your diode demodulator. Next, we go in for the procedures. Circuit connections are made as shown in the circuit diagram. The AM modulated waveform is given as input to the circuit. We can observe the demodulated waveform at the output of the diode, that is at the resistor point using a CRO. The various values of the modulating voltage, signal frequency, corresponding demodulated voltage and the frequencies are noted, the readings are tabulated. This is how your demodulation process is completed. So, this form we have already seen. We will be giving these 3 types of waveforms and we are going to drag the waveforms and pick up the envelope of these waveforms using the demodulation process. This being the input to the diode circuit, the output seen at the CRO will be like this. So, it will be small ripples, but more fruitfully the voltages, that is a message signal will be reconstructed back after the diode demodulator. This is also called as envelope detector. For the demodulator block, we have the given input as the AM modulated signal and the output is taken from the output across the load, that is a RL resistor. that value you can just see what is this. This is the message signal. We have set the message signal to be about 2 kilohertz, but because of the ripples and the RC time constant, this is measuring this. I just adjust the cursors to see the frequency of the demodulated output. V peak to peak value is about 640 millivolts. We can also see how intricately it has been by step it has been constructed back to get the maximum peak of the message signal, and it will be repeated, you can see it. So, this is how the diode will demodulate the message signal. So, the inferences are the amplitude modulation with the modulation index less than 1, equal to 1, greater than 1 is generated and observed. The AM modulated signal for modulation index less than 1 is demodulated using diode demodulator, and the message signal is observed. Finally, the result, thus the AM modulator and the demodulator is implemented and studied. So, this completes the study for AM modulation and demodulation in the lab. In summary, we have just seen the procedure to do it, values that are to be read and tabulated, waveforms that are to be seen and drawn, then the demodulation process with the procedure, the circuit ring up, the output waveforms, and then the inference and results. So, few questions you may try out and see in your lab. The audio signals are not transmitted by electromagnetic waves. You need to justify this statement, why they are not being transmitted. And what is the output power of an AM modulator? What will happen if the time constant of AM demodulator is less than inverse of the carrier frequency? Thank you.